Let's go to our solution for the next assignment. We will go to our classroom. In our classroom, we will go to the playlist. We're talking about generative AI. In this playlist, we are done with assignment 1, assignment 2, as well as we are done with video 5, which is Hugging Face models fine tuning. You must go through this assignment 3. Make sure that you watch all those 5 videos before assignment 3. Make sure that you understand this assignment and then try to attempt it a couple of times. Make sure that you give your best. If you're not able to get it, then only you watch this solution. First, before you go through this video, make sure that you try to do this assignment on your own. The problem statement is pretty straightforward. We will have one data set here. This is emotion detection data. And then we will use a pre-trained or pre-existing large language model, DistilBERT. We will use that model as it is first, and then try to get the predictions. Obviously, the predictions will be pretty poor because DistilBERT model will never get to know what is the actual data that we are handling. So it will give poor predictions. And then we will try to fine tune DistilBERT model by exposing our data. And then the model will adjust its weights, and then we will get the best accuracy from the pre-existing model. So this whole exercise is about fine-tuning the pre-existing large language model. So let us try to create a copy and try to solve this problem. Instructions are already given, various instructions, the problem statement, installation of the libraries, what all are required, and then importing of the data, using the model without fine-tuning. These are all the steps. And then fine-tuning the model with our data, load the model, train the model, make the predictions, make sure that you get the best accuracy. These are all the steps that we have to follow. Let us follow all these steps. First, we have to start with installation. So let us write the code for installation. We have to install transformers library. If we are working with Hugging Face models, we have to install transformers library. I will say pip install transformers, pip install accelerate. We have to install some of the dependencies as well, transformers, and there is a Hugging Face friendly datasets that also we need to install. Let me write that separately. Pip install datasets, and then PyArrow. I think after installing PyArrow, it will ask us to restart. I would like to tell you here that you must restart, otherwise you're going to face some errors later on. As of now, that looks like a requirement or a slight bug or something. Since we are installing Accelerate and PyArrow, we must restart right after this. In fact, in some of the systems, it will give us a pop-up saying that you must restart your system after installation. If it gives a pop-up, then we will try to restart. So let it install. It is going to take a couple of minutes of time. Let's wait for a couple of minutes for it to install. Usually, maybe this is the data set. Let's try to get the data while it is installing. This is the data set. Let's try to get the data. So this is the emotion data. So wget. So once you execute this piece of code, I think this will run only after executing the previous piece of code. Installing PyArrow, attempting to uninstall pips dependency, etc., etc. We are right at the end already. So it did not really ask for any reinstallation or the restarting, but I would still suggest you try to restart the session right after installation of those packages. Otherwise, I have observed sometimes we're installing Accelerate and PyArrow. Sometimes you're going to get an error later on. At that time, restarting and re-executing everything that we have executed until that point of time, that will be very painful. Even if you're not getting any pop-up here for reinstallation or restarting, go ahead and restart. And then we get this data set. This is the file, and then import pandas as a PD, and then we will try to get this data. Maybe let's call this as emotions data. This is how the data looks like. It is pretty straightforward data. We have the emotion and the text. This text is related to sadness. This text is related to sadness. This text is related to love. So if you want to see how many different emotions are there, looks like there are 5 different emotions are there. We can get a value count on that. Label is not defined. This is actually not the label. This is emotion, or we can also use label. L is lowercase there. Happiness, 10,000 records are there. Sadness, these many records. Neutral, worry, and love, these are the records that we have. Now what we will do is we will take the data as it is. We will try to use the DistilBERT model without fine tuning. This is the proper text classification model that is available on Hugging Face. You have multiple text classification models on Hugging Face. The model that we are going to use is this DistilBERT model. So you have several models. If you try to arrange them based on most downloads or the most votes, definitely you will see DistilBERT models being mentioned there because those are some of the best models for doing the text classification. But if I directly use that model on this data, the model will give me poor accuracy because it will be doing the basic classification for positive versus negative. But here our data is slightly different. The target variable is not having positive, negative, neutral classes. It is having happiness, sadness, neutral, worry, love. So it may not work well on this data, but let us go ahead, do our regular way of getting the model from Hugging Face and making some predictions. From transformers, Transformers is a package that will help us to access Hugging Face model, import pipeline. So my classifier, or let me call that as DistilBERT model or classifier, model name is this, task is this one. If you have CUDA, it's better to give a device equal to CUDA device. If you do not have CUDA, that is also fine. You can leave this particular sentence, this one, you can just leave it if you do not have CUDA. If you have CUDA, use it because it will make everything much faster. The whole classification will happen faster later on when we are using it on the data set for prediction. It will be happening much, much faster. This particular line of code that you can ignore. Right now, we are importing the model from Hugging Face. Now we will not work with the complete data. So this data has nearly, how many records are there? This has 10,000 plus 10,000. So nearly 50,000 records are there, or at least 45,000 records are there. And we don't want to work with all those 45,000 records. Let's work with randomly selected 10,000 records. That too, we will not work with this large text. Some of the text goes beyond the limit. Maybe we will take first 100 characters and then work with it. That should be sufficient because otherwise it will be a time consuming process. Maybe in version 1, we will try to work with the sample data and the sample portion of the text. Maybe in version 2, if we have sufficient time, we can work on the complete data. So my sample data that I want to take is from the emotions data, a sample of 10,000. Let us take 10,000 and then let's regenerate the same sample by using random state. This is the sample data that I have considered. Now within that sample data also, I would not like to take the full text. I would like to take only the text, which is the first 100 characters only. So let's write that. Consider first 100 characters only. So text, you can write it like this, or to be on the safe side, we can use like if there are extra spaces, we will try to remove those spaces and then we will try to consider the first 100 characters. Maybe just to be on the safe side, what I'll do is instead of writing X out of this, so first I will try to split X and then extra spaces, I'll just go one space. So the way you should do that is you do this way. So you say space dot join and then x dot split function. So what exactly is happening here? We will split x, we will split each of the text. We will split each of the text into words. And then if there are any extra spaces, we are going to replace all of them. So we are joining with spaces. Once you split it into words, and then by doing this, so extra spaces you will remove. Otherwise, you can directly use on X, you can take the first 100 characters, but this will be slightly a better approach. So you are taking the first 100 characters of the text. Now I will go ahead, apply BERT. So we will try to get the predicted values from the BERT model. The BERT model is a classifier. So let's get sample data. In that sample data, let me call it as BERT classifier or BERT predicted. Sample data text, apply lambda, classifier X. Basically, BERT gives us 2, 3 outputs. It gives us the label, it gives us a probability, etc. I will take only label out of that. You seem to be using pipeline sequentially on GPU in order to maximize efficiency. Please use a dataset, but that is fine. We will go ahead with this one. This also not going to take time. Since I'm using GPU, it will take a lesser time. But if you are using CPU, if you do not have GPU, you may expect this step to take a considerable amount of time, maybe 5 minutes of time. Here I'm expecting this to make predictions for the first 10,000 or for these 10,000 sample records. Maybe it'll take 1 minute or 2 minutes max. Still making the predictions. Let's wait for it to make the predictions. So it's done. Predictions are done. If you want to have a look at the sample data, you will have the emotion, which is the actual value, text, and then a label. Label is the target value. and BERT predicted. These are the BERT predicted label. I think it is giving label underscore label underscore. Let us remove that label underscore. Let us take only the last value, that is actual predicted class. So let's call that as BERT predicted number, BERT predicted numerical value. How do you do that? How do you take only the number out of that? So you will take BERT predicted, apply lambda. Well, this is too much. We don't need to do all of that. Apply lambda x, and from x, I will take the last character only. So if I do it this way, basically what this will do is it will go to every row and take only the last number, and we may have to convert it into numerical value as well. So BERT predicted numerical, otherwise it will be text only, is equal to as type integer. This is also fine, or directly also you can simply say, you can use as type integer. This is also fine. You can use both the ways. So I'm taking only the predicted value, which is a number only, not really the label underscore. This is BERT predicted and this is BERT predicted numerical. This is the actual value label. This is the predicted value. Now let us try to create the confusion matrix and see the accuracy. I am pretty sure this accuracy will be very, very low, because BERT will never get to know that, it has never got to know that we are working with emotion data. It never got to know that we have multiple labels in it. It has made a prediction about, I think, positive, negative, neutral, or positive and negative. So definitely we are going to get a very poor accuracy if you are using it without any fine tuning. So from sklearn matrix, import confusion matrix, this is the original value, actual value, this is the y predicted value. Now, if you want to print the confusion matrix, you can. So let's store it in confusion matrix. Let me call it as confusion matrix. Label is not defined. Let's call that as the label. So this is the data inside the confusion matrix. Definitely, it has very poor accuracy. If you want to calculate the accuracy directly, you can see there is everything is wrong about that confusion matrix. So accuracy score is equal to, you can do it this way, 0 0 1 1 2 2 3 3 4 4. That also fine. Otherwise, you can say confusion matrix dot diagonal elements dot. I think accuracy score direct option is also there. That can also be used. Any method is fine. This is the confusion matrix. This is the accuracy, and it is pretty poor accuracy. Only 25% is accuracy, and that is expected. We know that BERT model without any fine tuning on our data will give only this much accuracy. Now let's start the actual assignment. What we are really looking for in this assignment is fine tuning the model with our data. We will take the BERT model. We will tell that, please use my data, adjust your weights, and then try to make a prediction from 25% accuracy. We can make it above 80%. Then we can say that, yes, I can use this model. So there are a set of functions, there are a set of libraries that we have to get them: tokenizer function, sequence classification, etc., trainer arguments, all of them. Let us get them. From transformers, get the DistilBERT tokenizer, DistilBERT sequence classification, as well as a trainer. There is one function, or let me write that separately. From transformers, import trainer function, trainer arguments, and trainer. From datasets, import a load dataset, dataset dictionary, class labels, and then dataset. Train test plate, yes, pandas we have imported, and torch, as well as everything. All these are required, which we will be using. So let's take the sample data. So we already have the sample data, but we have to convert it into Hugging Face friendly format. So for that, we have to use this data set from pandas, the original sample data that we already have. This is the sample data, which will now be converted into a different format altogether. If you want to have a look at the, let's call that as Hugging Face sample data, or for Hugging Face, this is Hugging Face friendly sample data. So it looks like this. Original pandas data frame looks slightly different. This one looks a little different because it has several other parameters. It has several other objects in it. This is the format that we have to convert the original pandas data frame into before doing the fine tuning. Then once you convert it, then you will do the train test split, train test split, train data Hugging Face, test data Hugging Face. You would say sample data. You can do it this way, or we can simply say train test split and then use it later also. This is one way. But the usual approach that I have seen is people say train test split is equal to your dataset name, which is Hugging Face, Hugging Face data, and then train test plate, and then you say test data size equal to 0.2. This will be particularly useful later on because if we are storing the data in the form of dataset dictionary, that will be later on when we are doing the fine tuning. This format will be pretty useful. So you will say my dataset is equal to dataset dictionary. My train data is the train data set. In the train test split, there is something called train data. That's the one. My test data is this one. The reason why we are doing it this way is later on, whatever tokenization, whatever task that you want to apply on the train data, if you want to apply parallelly on the test data, by accessing the data set, you can do it in one shot. So data set is a data set dictionary, like the one that we have created. It's a dictionary which is having both train data as well as the test data. So later on, you can use, like, if there's an option or if there's a requirement for you to apply some action on both the data sets in one go, you can use this particular data set, which is binding train and test data together. If you want to do it individually, that is also fine. You can access only one data set out of that. So this is the data set which we have converted into Hugging Face friendly dataset format. The action has not yet started. Now let's start the tokenizing. So my tokenizer is DistilBERT tokenizer. First declare tokenizer as DistilBERT tokenizer from pre-train, DistilBERT uncased. And then if we want to do padding, we will do it separately. First, we will try to load this. Tokenizer is done. So let's do the padding part. Padding means like if we want to restrict it to a certain length, then we can restrict it to that length. So my tokenizer dot pad. This is the option for padding. Basically, we are going to add extra zeros either at the beginning or at the end. We can say end of the sentence or beginning of the sentence. Now this is the tokenizer function and we have added the padding function also. This is optional. It's not really required, but let us try to finally create the tokenize function. We will define one function, tokenize function. We will take all the text as the input and we will try to return the tokenizer example text, and then padding, whatever is the max length, we are defining the max length as 100 and the truncation is equal to true. If we want to truncate the text that is going beyond the length of 100, we would like to cut it down. And then finally, we want to apply this particular function. So my final tokenized datasets, I will go to dataset, which is the dataset which is having train and test data, map tokenized function. This is the function in batch format. It is true. That means one by one batch. If you want to do it, that is also fine. Otherwise, that is an optional one. So what we are doing is we are simply tokenizing the data. We are converting the train and test data into sequence of numbers. Tokenization is done. Padding is optional. If required, we can do it. Otherwise, we can ignore that padding as well. So once you have the tokenized data, we will load the model and then we will try to fine tune the model. So let us load the model and train the model. Already instructions are given here. If you follow those instructions, what it is trying to tell us is my model is equal to DistilBERT for classification, and this is the model name. And this is the parameter that you must give. How many classes are there in the target variable? Number of labels are 5 that you must give. Pad token ID equal to tokenizer, end of the token ID. That's what we are giving here. If you want to adjust the number of labels depending on your problem statement, you can, but here we have 5 of them. So this is the model that some of the weights are etc etc. You should probably train the model etc. This is the usual notification that you will get. Now let us create some training arguments. Training arguments are equal to training arguments. Where do you want to store your model? This is the place I want to store the model. Number of training epochs equal to 3 or 5 depending on what are you executing. Maybe go with one epoch. Later on you can increase the epochs. Where do you want to store the logs while building the model? In one of the directory. Evaluation strategy epoch means epoch by epoch I want to evaluate and look at the train and test accuracy. Future warning, evaluation strategy is deprecated and removed. Eval strategy, it should be eval strategy instead of evaluation strategy. It looks like that is deprecated. And then we will try to initialize the trainer. We will say my trainer is equal to trainer, use my model, use the arguments, use the train data, and use the test data from the tokenized data sets. Tokenized data set from there, use the train and test data. Now, once I say trainer dot train, it may take some time. Trainer dot train, since we are doing it on CUDA, it should take lesser amount of time. So I'm running it for 5 epochs. So right now it is in epoch 1. It is taking some time. Let it take time, no problem. Overall, I think 5 epochs is going to take roughly 5 minutes of time. That's what I'm guessing. Let us execute it. If you're working on CPU, it may take even more time. Overall, it took me around 4 minutes, 54 seconds for executing 5 epochs. Let us try to see with this new model, what is our accuracy. Let us try to save this model. Let's say our model directory is DistilBERT fine-tuned. We can save the model. I think for saving the pre-trained model, we have to use this save pre-trained function and then give the model directory, save the tokenizer. Now, these are all optional steps. If you want to skip them, you can skip them because directly our model is ready. We can use it. But if you want to take this model, keep it somewhere else, or if you want to give it to someone else, or if you want to refer to this later on physically, if you want to save it, then we can use these steps. Trainer, save the model. You can give the model directory, or you can give some other name as well. Let's say, let me call this as custom model. With 10K records, we have used 10,000 records. So once you do this, the model has been saved. You can see that custom model 10K. This is the model.save tensors, binary file model.bin, and this is actual model 255 MB is the size of the model that we have already trained. Now, if you want to have a look at the model, you can have it. But before that, let us try to make the predictions using this model. Predictions are not straightforward. We have to create a function. We have to create a function for making the predictions. Let us try to create that function. Def make predictions function. Take the text as input and then first tokenize it. Return tensors equal to true, padding equal to true, truncation equal to true. These are optional since anyway in the tokenizer we have defined them. So you can ignore these. Directly return tensors equal to kind of PT. And then inputs, if you want to load them to CUDA, that is fine. Otherwise, this is also optional. You can ignore this for now. That is also not required. Model, get the inputs, all the inputs. Then make the predictions here. The predictions happen here. And prediction will not give you directly the predicted class. You have to get the predicted values and then get the argmax. Or here we are storing them as outputs. So we have to say predictions are equal to outputs and then dot logits, then argmax value. So the class that is having the maximum probability will be returning the values. And then finally, we are getting the predictions. Directly, we can give the predictions also or from the CPU. I think we are already working on CPU. This is not required, but since we are using return tensors and so on, that is why we have to do it this way. Or let us write one extra step, which is like our predictions. Return predictions should be fine. Let's try this. If this doesn't work, then we will try to get from the CPU. So this is the function. The model that we have already seen, model was built here. Trainer.train model is the model name. DistilBERT fine-tuned model is what we are going to use right now. Now the sample data. In the sample data, I'm going to create fine-tuned predicted with the new model. We are going to make the predictions, apply lambda, make predictions. And then from the predictions, like make sure that you are giving the text only as input. Just to be on the safe side, I'm converting everything as string. And then from the predictions, we would like to take the first value only, which is already there. Incomplete one, creating this one. Yes, we have to give one more. Expected all the tensors to be on the same device, found two devices, CUDA also found, and this is also found. So since it is not working, what we will do is we will detach them from the CUDA. So what we will do is we will say my predictions are detached, and then I will try to return only the predictions. Predictions, and then return only the predictions. Now that should work. Similar error, exceptional errors, CUDA. Let us load them to CUDA first. I would say my inputs equal to inputs to CUDA. Or do we need to write torch dot device CUDA sometimes? So I've loaded the inputs to CUDA and then got the outputs, and then I have detached them, and then I'm giving the final predicted values. But these predictions, I think it will give 2, 3 values. We may have to get only the first prediction, but let us see what are all these sample predictions look like. Maybe what we will do is just to see how is the final predicted value or one predicted value look like. We will do a sample from the sample data. We will take the head only or the first few records. Sample data temporary data set is equal to sample data dot head, only 5 records we will take, and then try to get the predictions. How do they look like? Just to make sure that everything is working fine, because this step is going to take us some amount of time for making predictions. That's why we will take only sample data temp and then apply this. So 3, 4, 4 like that it's giving, which is not bad, but it is giving in this manner. So what we will do is to get only the exact predicted value instead of the array. If I want to get exactly the predicted value from this make predictions, I would like to take the first element of that. So this is what exactly we are looking for. So let me put the first element of that array or the list. So this is just a temporary data set that I have created just to make sure that the code is working fine or not. Once the predictions are made, we will be able to create the confusion matrix and find the accuracy. It is going to take some time, this particular step. We got the predicted values. It took around 1 minute, 12 seconds for execution of that whole predictions. If you want to have a look at the fine-tuned predicted values, there will be zeros and ones and twos and threes. Until 4, there are 5 categories in the target variable. Now it's time for us to create a confusion matrix and check the accuracy. Earlier, the accuracy was pretty bad, 20% accuracy. Nowhere the model was good. Now that we have exposed our data to this DistilBERT model, and the model has taken our data, adjusted the weights, we have run it for 5 epochs for 10,000 records. Let us see what is the result like. So from sklearn matrix, import the confusion matrix, and then this is the actual class, and this is the fine-tuned predicted class, and then this is the confusion matrix and the accuracy. We are expecting much, much better accuracy. Now, as you can see, the accuracy from 20% has improved to 88%. Definitely, this is far better model. Already, this is a large language model, which is very powerful. What we have done here is we simply exposed our data so that the model understands it is working for this particular data set. So this is one way of dealing with hallucination, or this is one way of making the model work the best on our particular data set. This is the Hugging Face fine tuning. If you want to import this data, if you want to give it to somebody, we just need to take this particular model, zip it, and then take it to, like, later on if you want to keep it somewhere. So you can use, let's say, if you zip this model and send it to someone, if they want to access it, they can simply say model underscore version 1 is equal to, you will say DistilBERT for sequence classification from pre-trained. You mentioned here, instead of any other parameter, you mention here whatever is the location. Copy the path. Anybody who takes this model, once they keep it in their system, they should copy the path and simply say this is sufficient. Once you do this, they will be able to access the model. This is model version 1. Now you can load that model to CUDA and work. You can make all the predictions whatever you want. Now this is the model with these many embedding layer, with these many parameters and these many nodes. This is a quite a huge model. Obviously, it's very difficult for us to build a large language model like this, but we can always fine tune the pre-existing model. So we can use this model. Right now, we have fine-tuned the model only using 10,000 records. What I encourage you right now is go back to the place where we have taken the sample data, and then try to take, instead of 10,000 records, take many more records and try to make this model much, much better. Right now, we are working with only sample data set. On that sample data set, it is doing good. You can repeat the same process for the larger 40,000 records or 45,000 records that are given here. So that is it with this particular assignment. And once again, once if I'm coding it here, I may be comfortable, but if you are from your side, you may not feel really comfortable unless until you practice it multiple times. There are so many nuances, there are so many finer details that we may have to learn before coming to this particular assignment. Make sure that you complete all of them. Then I'll see you in the next class. And then after a couple of classes, again, there will be an assignment. First, you attempt that assignment, make sure that you try your best, and then you come for the solution. I'll see you in the next session.